This is a demo of RAN slicing on software-defined radios and compute resources running in the Powder Wireless Network Testbed at the University of Utah. My name is David Johnson. I'm a researcher in the Flux Research Group in the School of Computing at the University of Utah. The context for this demo is RAN slicing in an Open RAN implementation. At the top of our stack, we're using ORAN. The ORAN Alliance has developed a reference implementation of a cloud-based Open RAN implementation. We're focusing on the RAN intelligent controller for this demo, as well as RAN resources that run on software-defined radios that have been enabled to talk to the ORAN RIC. In particular, we've modified SRS-LTE with ORAN RIC support. So it supports the ORAN E2 protocol, which you see in this figure, that connects down to a CU or a DU in 5G terminology. Or we've also modified, since we're using SRS-LTE and 5G is still in development in SRS-LTE, we've modified a 4G eNode B with ORAN support. The RIC, the RAN Intelligent Controller, is envisioned to be a collection of microservices running in a cloud that has near real-time access to these radio resources. And the RIC can host applications, third-party applications, which are called XApps. We've also written a custom XApp that implements RAN slicing by sending instructions to RAN nodes to perform custom resource allocation for slices and bind UEs to those slices. We've done this just by modifying the eNode B parts of SRS-LTE and implementing our own scheduler within SRS-LTE using the existing SRS-LTE round-robin scheduler. As I said, we're going to be running this inside of the Powder Wireless Network Testbed. In Powder, it's easy to reserve radio and compute resources to perform experiments by defining first a profile that describes the resources that you need and instantiating that to bind it to real resources. All of this happens automatically once you've defined your profile, and your experiment can swap in a matter of minutes. So I'll have two experiments shown in this demo. One is you can think of it as the ORAN cloud. It's a single node that's hosting a Kubernetes installation with ORAN components deployed inside. And inside of that ORAN deployment, then we'll be running a custom XApp. That is the XApp that we wrote to control the slicing happening inside of our node Bs. So that's this first experiment. Powder experiments can have custom instructions written for them. The instructions for this experiment describe how to run this demonstration and how to access ORAN. So let's take a look quickly just to ground ourselves at what ORAN looks like running inside of a Kubernetes instance. So I'm going to copy this per experiment random password that will allow me to log into my Kubernetes dashboard. And I'll do that now just so that we can get a quick look at what ORAN looks like. So this is just the Kubernetes, the standard Kubernetes interface. There are several namespaces where components are deployed. I'm going to go and look at the RIC platform components. Here I see a number of deployed pods that correspond to the ORAN microservices. The details here are not important. It's just that there are a collection of them running. My second experiment is my RAN resources that I'm going to connect to my ORAN cloud and to my XApp that's running inside of ORAN. So these are three radio resources. These are all NI B210s inside of the Powder Wireless Network Testbed. You can see that I have one node that's acting as an eNode B, and I have two nodes that are acting as UEs. They appear to have connections. They appear as part of a graph because these B210s are attached to a wireless network emulator that is emulating channel paths between the node B and the UEs. Finally, There's a connection that appears to go nowhere, but that's my wired connection over to my other experiment, so that my node B can be placed into contact with the ORAN RIC core running inside of the Kubernetes instance in the experiment that I toured previously. This experiment also has instructions for running demos. Let me move over to another part of my screen here. And I should also say, before I do that, I should say that these resources are available for login. These are Linux servers. In this case, this is a high-powered many-core machine with significant amounts of memory, which is why we can run an entire Kubernetes as well as microservices and the XApp on it. And I can click to log in. I can start up a shell if I want to, and do that. So I've got all of those things set up in another tab to the right, which I'll flip to over here now. So I've got basically 4 quadrants of my display here that I'm going to be running. First of all, I'm going to focus on my RAN resources. In my upper left terminal, I'm going to start up my RAN core. So I'm going to start up an EPC. Again, this is using SRS LTE. We didn't modify the SRS EPC parts of that. Then I'm going to start up my eNode B. I already have my RIC deployed. I'm not going to show the deployment of all of that. That's automated by the deployment automation we've built into our ORAN profile. So I'm attaching to my B210 here, and you can see that there's some XML-ish output that's coming across. This is the connection establishment with the E2 terminator inside of the ORAN RIC. So my node B sent a setup message and received a setup response. Part of that setup message was for the node B to advertise which kinds of ORAN services it exposes. So inside of the RIC and in the XApp ecosphere, services that RAN elements expose are defined by service models. So we've built our own service model that defines RAN slicing and resource allocation. And we're still working to extend and evolve that. So the setup messages are telling the ORAN RIC what kinds of services my node B exports, so that XApps, when they start up, can consume those services. They can send control messages to my node B to request that it perform remote functions, or they can subscribe to messages such as status updates or event notifications of things that happen. Suppose that a new UE attaches to my eNode B and I want my XApp to know about that. I can model that as a publish-subscribe interaction. Okay, so I've got my node B running. I'm going to go ahead to over to the right-hand side of my screen, where I've got basically my UEs. I've got my first UE here in the middle, and then my second UE over here on the far right. I'm also going to run some iPerf servers, because we're going to demonstrate the RAN slicing by looking at available bandwidth changes on these UE to eNode B links. So I'm just going to start up simply my UEs. And you can see that they're both going to connect to my node B on the left. I'm going to flip over and fire off some client iPerfs. So you can see my iPerfs running over. I'm going to flip back to my node B here so you can see its output. But you can see that my UEs basically have the same bandwidth, running around 17 point something megabits per second. By default, they're not bound to any slice, so they're just running in the default slice. Our resource allocation scheduler by default is work conserving. So even though the default slice has a low proportion of resources that are allocated to it in the presence of slices that otherwise do have resources allocated to them, since it's work conserving, the full set of bandwidth that's available in this, based on how I have the node B configured with the number of PRBs that it has, is available. So the two UEs are just splitting the bandwidth right now. Now, in my lower left-hand window, that's kind of my view into the ORAN world. So I can show you the output of some of those pods and containers. We can take a look at, for instance, our E2 manager, which is managing different parts of the E2 core. I can take that was the E2 termination service, which is what connects the ORAN E2 protocol. It connects the ORAN RIC to my RAN nodes over the E2 protocol. I could also look at my E2 manager and look at the messages that are flowing across that. And finally, I could look at a number of components, but I can also view quickly my subscription manager. So if my XApp subscribes to my node B to receive notifications about services that node B is providing, the subscription manager plays an integral role in that. I'm just going to leave my E2 manager running here. And then I'm going to, actually there's one other piece I could show, which is the app manager component. This is where I would, this is the component that's responsible for XApp deployment on the RIC. So I already actually had an instance of my XApp running, so I'm going to go ahead and delete that now. And then I'm going to recreate it quickly. So that's the information that you're seeing scrolling here. It's a lot of JSON, so the app manager is configuring Helm charts in the background, and it's deploying this. So now I'm going to go take a look at the logs from my XApp implementing XApp, and our XApp is simply called NextRAN. And it has both what you can think of as a southbound interface to the RIC. This is how it sends messages down to the RAN nodes to change their slicing allocation. And it has a northbound interface it's a RESTful northbound interface that allows me to issue high-level commands to allocate slices, to tell the XApp about node Bs and UEs, and to bind slices to node Bs, and then to bind UEs to the slices that I want them to be in, as well as dynamically changing the slice resource allocation parameters. I'm going to be issuing those commands in this final terminal in the lower right-hand part of my screen. So I've got my XApp running. You can see that it's exchanging messages with the E2. The details of that are not important. Now, I'm going to send these simple RESTful commands using curl commands, and then we'll look at the output. So first, I need to get the IP address of my app that's running inside of Kubernetes. So now that I've done that, I can ask my app what node Bs it knows about, and it doesn't know about any node Bs. So let's go ahead and tell it about the node B that I have, that I started earlier. And I happen to know the identifying details of that node B. So now I can go back and look, and now I see that there is actually a node B that I've told the XApp about. Now I'm going to go ahead and create some slices. So I'm going to create a fast slice and a slow slice. Here's my fast slice. So my fast slice has a simple allocation policy. This is a fairly simple scheduler that we've implemented. It's just a proportional scheduler. So shares are expressed in the range of 1 to 2 to the 10th, so 1024. And I am going to then create a slow slice here, and the slow slice just has a relatively smaller amount of shares, so we're giving a share of 256. Okay, I'm going to bind the fast slice to my node B, so now you're going to see some output in the upper left terminal at my node B. This is again an XML version of an ASN1 encoded 3GPP-ish message that is telling my slice scheduler about the fast slice. So you can see that the slicer now knows about a fast slice, and it has a high proportion relative to the default slice, which has a very small allocation, just enough to allow control PRBs and a very small amount of data. Then I'm going to bind my slow slice over to my node B as well. So I'm sending a simple command that binds my slow slice over, and let me scroll the output. So now there are several slices. There's a default slice, a fast slice, and a slow slice. And the slow slice has a slightly larger than default allocation, but much lower than the fast slice. Now I'm going to tell my XApp about my UEs. So I already have my UEs running. I know what their identifying information is. So I'm telling it about the IMSI of those UEs. I'm going to go ahead and create my second UE, tell my XApp about that. And then I'm going to bind my UEs to slices. So keep in mind, you're going to be watching for the throughput change on my UEs. First, I'm going to bind my first UE to the fast slice. And you can see that the bandwidth has gone up quite dramatically for the fast slice, and the slow slices the unbound UE is getting a very small percentage of the bandwidth. Now I'm going to bind my second UE to the slow slice, and it's going to get a slightly increased amount of the bandwidth. And so there's about 34 megabits available in this particular configuration, and you can see that my fast slice has achieved a relatively high bandwidth. Now I'm going to go ahead and change the allocation of the slow slice. In fact, I'm just going to bring it up to parity with the fast slice. So you can see that I'm issuing a put command to my XApp, and my XApp is going to send that down to the node B, and you can see this message has been sent to the node B. It's reconfigured the slice. You can see that the throughputs are equalizing. I can go ahead and do that again. I can change the slow slice to have a medium share of the bandwidth. Let's say 512. And I can use this XApp to unbind my UEs and rebind them to a different slice. I can delete them or delete slices and add more slices and change the binding that way. But this is just a simple demo, and this is kind of the conclusion of the demo. I've just demonstrated some throughput control with my slicing implementation. Let me scroll back over here. So you can run these demos in the Powder Wireless Network Testbed today, and the software is freely available. We have our modified version of SRS LTE that's available. That's also linked from these Powder profiles that you can instantiate today. And our implementation of the NextRAN XApp that we designed and built is also freely available, and it's part of the ORAN profile. So it's very easy to run this stuff in the Powder Wireless Network Testbed. I would encourage you to go to powderwireless.net and sign up for an account and try to run these demos. Thanks very much for watching.